Good morning, all students. In yesterday's lecture, we started this part of inner transition elements. These inner transition elements are also called as F block elements because outermost electrons enters in F orbital, which is pre-penultimate shell. Last shell is ultimate shell. Before the last shell, there is a one shell. It is called as penultimate shell. And this F orbital is inside the d orbital. It is called as pre-penultimate shell. Remember, so if the definition is asked for the examination, we have to write in case of F block elements, the electron enters in F orbital, which is pre-penultimate shell. So once again, I will take the quick revision of where the position of F block elements, where the lanthanide series and actinide series, these two series are called as F block elements, which are placed for convenient purpose. These are placed below the periodic table. Actually, these are present. Lanthanides are present in group number 3. Clearly, we can see. Yes. So the position of lanthanides is group number 3 and period number 6, and the position of actinides is group number 3 and period number 7. So lanthanide starts from 57 to 71. First element is lanthanum, and last one is lutetium. Actinide series starts from 89 to 103. So first element is actinium and the last element is lawrencium 103. Yesterday we also discussed the general oxidation state of this lanthanide is generally shows +3 oxidation state, but this europium and this ytterbium shows +2 oxidation state. These shows exceptional. That's why they also behave as a alkaline earth metals. And this cerium shows +4 oxidation state. This part is completely completed yesterday. Also, one important characteristics of this lanthanide is lanthanide contraction. Because as the atomic number increases from this 57, 58, 59 to 71, actually there should be increase in atomic size. But it is observed that instead of increasing the atomic size, atomic radii are decreasing, ionic radii are also decreasing. This is happening because of lanthanide contraction. And what is this lanthanide contraction? As the electrons are added in the same shell, what is happening? The nuclear charge is increases, and the nucleus will pulls the electron towards itself. So the atomic and ionic radii are decreases, means the effect of nuclear charge is more than the effect of shielding effect, because shielding effect, as you know, in case of lanthanides, electron enters in 4f orbital, and in case of actinides, electron enters in 5f orbital. So in lanthanides also and actinides also, there is a contraction. In case of lanthanide, it is called as lanthanide contraction. See, it is shown here, the lanthanide contraction, and in case of actinides, it is called as actinide contraction. That is the decrease in, if you see in this table, it is shown from this lanthanum to lutetium, this atomic radii are decreasing. This lanthanum, then gadolinium and this lutetium, they acquires the extra stability because this 4f orbital is half filled. We can see here, this is 0 electrons, means there is a so this lanthanum and gadolinium and lutetium, see the electronic configuration, there is no any electron in the case of F. In case of gadolinium, there are 7 electrons, and in case of lutetium, there are 14 electrons. So These are more stable. They acquire extra stability when the f orbital is half filled. So it is shown the general electronic configuration of lanthanides. You can see xenon. This is electronic configuration with respect to inert gas. Means first electronic configuration of xenon is included in the bracket. 4f 0 to 14. 0 to 14 indicates means 4f 1, 2, 3, 4, 4f 14. 5d 0 to 2. In case of this lanthanum only, gadolinium only, and lutetium only, the d orbital contains one electron, we can see. Otherwise, in case of all the elements, the d orbital is empty. 5d0, 5d0, we can see clearly. So this lanthanum, gadolinium, and lutetium, they possess only one electron in the 5d subshell. Otherwise, the d orbital is empty in all the lanthanides, and this is due to the extra stability. To acquire the extra stability, there is one electron in case of gadolinium and lutetium, and in case of lanthanum. Then I am coming to the ionization energy values. You know the definition of ionization energy. Ionization energy is also called as ionization enthalpies. It is nothing but the amount of energy required to remove most loosely bound electron from its outermost shell in the gaseous state. It is called as ionization energy values or ionization enthalpy values. In case of transition elements, also we discuss this definition. So it is exactly opposite to the atomic size. If atomic size is less, then ionization energy will be more. If the atomic size is more, ionization energy will be less. This is due to the when atomic size is less, the electron will closer to the nucleus, and if it is closer to the nucleus, more amount of energy is required to remove the electron. And if the electron is away from the nucleus, then it will be easily removed. It requires less energy to remove the electron. So always remember, these ionization energy values are exactly opposite to the atomic size. So you know the contraction takes place as the atomic size is decreases, ionization energy values will be increases. So the first ionization enthalpy values increases with increase in atomic number. This is due to the lanthanide contraction. So in this table, this IE1 indicates this is the first ionization energy values, IE2 this is the second ionization energy values, and IE3 this is the third ionization energy values. You know, the second ionization energy values and third ionization energy values are always higher because stability, as the stability increases, it requires more energy to remove the electron from the outermost shell. So these values are not expected from the students, only the trends are expected. What is happening in case of first ionization energy, what is happening in case of second ionization energy, what is happening in case of third ionization energy. So these values will not be asked for the examination, but the trends are asked. That's why it is noted here, values are not expected from the students, only the trends are expected. So for the board examination, this question will be asked. Explain the periodic trends or periodic properties of ionization enthalpy values in case of lanthanides. So these elements are also not required from the students to remember. Only we have to write from this lanthanum to lutetium. This is a first element is lanthanum to last element is lutetium. What is happening? The ionization enthalpy values are increases. But in case of, we can see lutetium, these ionization energy values decreases. The same reason like zinc. In case of zinc also we can see the ionization energy values is less because in case of lutetium, if it is completely filled, 14 electron there, the force of repulsion is more than the force of attraction. So atomic size is quietly large, so amount of energy required will be less. So this is a exceptional, lutetium is exceptional, like zinc also. Zinc, mercury, cadmium, we already discussed in transition elements. Oxidation state is I completed this oxidation state. Again, I will explain the general oxidation state of these lanthanides shows +3 oxidation state, remember. So +3 oxidation state is more common, but there are some elements. And the two elements are ytterbium and europium shows +2 oxidation state. And only one element shows +4 oxidation state. That is cerium shows +4 oxidation state. There are some examples. See, the cerium shows +4 oxidation state when there is no any electron in case of f orbital. Europium shows +2, ytterbium shows +2, and this terbium shows +4 oxidation state when there are 7 electrons in the f orbital. So this terbium also shows +4, but there are 7 electrons. We can see this terbium +4 here. See, so this terbium, it is having the electronic configuration 4f9, 5d0, 6s2. These 2 electrons will be removed. It will be +2, and then again 2 electrons will be removed from this 4f. So if this 4f contains 7 electrons here, if this 4f contains 7 electron, then this terbium shows +4 oxidation state. Now I'm coming to the color and spectra. Some trivalent ions means in case of +3 oxidation state are colored in solid state as well as in solution, like D block elements. Once again I am repeating here, because the color of the transition elements depends upon the 4 factors. The 4 factors are: first one is the number of unpaired electrons, second factor is the DD transition, third factor is nature of groups which are attached, that is the nature of ligands which is attached to the central metal atom, and number 4 was the geometry of the complex. And one additional point is there on which the color of the transition elements, I am talking about the transition elements, remember, though charge transfer is there. And the good example I explained 2 times, that is KMnO4, it is having the intense purple color, that is because of charge transfer, remember, in which the charge is transferred from oxygen to the manganese. O2 2 minus becomes O minus, and oxidation state of the manganese +7, it is changed to +6. Remember this example. But I am coming to the lanthanides. In case of lanthanides, +3 oxidation state. This shows colored in case of solid form and in case of solution. And this color is due to the FF transition, remember. So in case of transition elements, it is the DD transition. In case of lanthanides, it is FF transition, means again the electron absorbs the energy from the visible light and it will be excited. So the detailed explanation is not given in case of F orbital because there is more complications are there. The color of the ions having the NF electrons is about the same, those having the 14 minus NF electrons. So the splitting takes place there. And some colors are shown. This is not expected from the student point of view. Which colored for which ion, this is not expected. Only why the colors are there, it is expected. So the lanthanides having the colors due to the FF transition, remember, FF transition. Then this is a lanthanide contraction, detailed, it is explained here. Lanthanide contraction, this part is very, very, very important regarding the board examination, because this questions, it is a favorable question of the paper setter, remember, where for 1 mark or 2 mark, for 3 marks, this question will be asked. So if the lanthanide contraction, it is asked for the examination, what is mean by lanthanide contraction, write its effects and write its causes. This question was very favorite. So lanthanide contraction means contraction, you know, contraction means decrease, decrease in atomic size. But this decrease in atomic size with increase in atomic number, this is called as lanthanide contraction. Remember, as we move from as we move along the lanthanide series, that is from lanthanum to lutetium, there is a decrease in atomic and ionic radii. This steady decrease in atomic and ionic radii, it is called as lanthanide contraction. Remember, if this is asked for 1 mark for the definition, only we have to write down. With increase in atomic number in lanthanide series, if you remember the name of the element, it is better from lanthanum to lutetium. Or if any student forgot the name of the elements, he can write, in case of lanthanide series, from first element to the last element, as the atomic number increases, there is a decrease in atomic radii and ionic radii. This phenomenon is called as lanthanide contraction. Remember. So we will get 1 mark here. And why this is happening, lanthanide contraction? Because as I explained earlier, there are 2 types of effects. One is a shielding effect, and another effect is nuclear charge effect. So as we move from this lanthanum to lutetium, what is happening? The nuclear charge is increases. This nuclear charge will be increases because we are adding the electron in the 4f orbital, 4f1, 4f2, 4f3, 4, 5, 6, 7, 8. We are adding the electron in the same shell, and what is the effect of this electron? The nuclear charge will be increases on the nucleus. So if the nuclear charge increases, it will pulls the electron towards itself. And what will happen? There will be the contraction takes place. So the nuclear charge effect is very strong, but another effect is also present there. As the electron is present in F orbital, there is also the shielding effect. But the shielding effect is very poor here because the electron enters in 4f orbital. So the nuclear charge effect is strong and the shielding effect is very weak. That's why the contraction takes place, remember. If the shielding effect will be more than the nuclear charge effect, then atomic size will be increases. But this is not happening. Nuclear charge effect is more strong than the shielding effect. That's why the contraction takes place, remember. So this phenomenon is very important. Why the contraction takes place? Only one reason is there. Nuclear charge effect is more strong than the shielding effects. So the contraction takes place, nuclear will attract the last electron towards itself, and the atomic size will be decreases. This is the reason. So it is explained here, the new electrons are added in the same 4f orbital, so the nuclear charge will be more, and the shielding effect of this 4f orbital is very, very poor. This is the reasons are given why the lanthanide contraction is takes place. So this is graphically shown how the ionic radii are decreases here. This is graphically shown. See, we can see the graph. From this lanthanum, it is 106, and as we move to the lutetium, it is decreases. In this table also we can see it is shown. In this table also it is shown. Ionic radii decreases. See, from 106 to 86. So it is not expected to draw the graphs also. Only remember the definition. Again, there is a definition is given 3 or 4 times because of importance. This contraction is important. The atomic and ionic radii of lanthanide shows gradual decrease in atomic size with increase in atomic number. This is called as lanthanide contraction. Now, this causes of lanthanide contraction is just explained why this contraction takes place. Now I will explain the effects of lanthanide contraction. These effects of lanthanide contractions are not given in your textbook. Means there is no any special, what you can say, specially it is not given, but in the properties of lanthanides, it is given only the basicity decreases. We also discussed this point during the properties of lanthanides. But in detail for you only, I have prepared this slide. What are the effects of lanthanide contraction? First effect is decrease in basicity. Means basicity decrease as the atomic size decreases, the basicity will also decreases. So lanthanum hydroxide, LaOH thrice, this is a strong base, and lutetium hydroxide, LuOH thrice, this is a weak base. These reasons are given why the basicity is decreases, but this is not expected. Only at the time of the board examination we can write due to the lanthanide contraction, the size of the trivalent, this size of the trivalent ions decreases from lanthanum to lutetium. So this size is decreases. So according to the Pajan's rule, this is not expected to write. I have given this for your understanding purpose. Why? What is the effect of the size of the cation and basicity? So this explanation is given for your understanding only. As the size of the cation decreases, means the size of La3 plus is very large, and the size of plutonium 3 plus is very less. So this Fajan is the name of the one scientist. According to this Fajan, as the size of the cation decreases, the polarizability increases. So this polarizability increases, and thus the covalent character this of MOH bond increases. Where M is a metal and this OH is hydroxide, metal MOH bond will be increases, and the ionic character will be decreases. Means the covalent character will be increases and the ionic character will be decreases. If you understand, then it is well and good. If you didn't understand, forget about this Fajan's rule, because this is not expected to write. Only we have to write due to the decrease in atomic size, the basicity also decreases. So LaOH thrice, the lanthanum hydroxide is a very strong base, and this lutetium OH thrice, this is a very weak base. And another important effect there is a happening in case of lanthanide contraction. So what will happen due to this lanthanide contraction? The elements following the lanthanides in the 6th period are called as post-lanthanoids. I will show with the help of this graph, with the help of this periodic table it is given. See. So this elements, hafnium, yes, these elements are called as post-lanthanide elements. Means the elements came after the lanthanoids. These elements are called as post-lanthanoids. So what is happening due to the lanthanide contraction? This is a lanthanide series from lanthanum to lutetium, and these elements are called as post-lanthanide element. There is hafnium, then tactinium, then tungsten, this osmium, platinum, EUHG. So what is the effect of this lanthanide contraction? Its atomic size is also decreases. This atomic size of the post-lanthanides is also decreases, and it will be equivalent to the 5th period. Means the atomic size of this zirconium, which is having the atomic number 40, and this hafnium, which is having the atomic number 72, these are having the similar atomic size. So this zirconium, hafnium, this niobium and tactinium, then this molybdenum and this tungsten. So what is happening? Due to this lanthanide contraction, the atomic size of the post-lanthanides is also decreases, and it becomes equivalent to the elements which are present in the 5th period. So they forms chemical twins. Chemical twins means these are the twins prepared because they having the similar chemical properties because of the same atomic size. So this decrease in atomic size of the post-lanthanoids, who is responsible for this lanthanoid contraction is responsible. So this zirconium, hafnium, these chemical twins are prepared. So twins are nothing but due to the same atomic size, this zirconium, hafnium, this NiONbTA, molybdenum, tungsten, these chemical twins are prepared. So again, I am coming to this this effect. So this effect is very important effect due to the lanthanoid contraction. The atomic and ionic radii of the post-lanthanoids are similar. So this hafnium, zirconium, we can see Ta, Nb, tungsten, Mo, Re, Tc, which forms the chemical twins. It is given here. So pairs of these elements, zirconium, hafnium, this Nb, Ta, molybdenum, tungsten, Tc, Re, which are in not in the same group, but these are in present in different groups. So they forms the chemical twins. So this chemical twins question, it is asked for many times for the board examination. What is mean by chemical twins? It is given in only one line. But these twins are prepared due to the lanthanoid contraction, remember. And they possess the almost identical sizes and the similar chemical properties. So the effects of lanthanoid contraction, first effect is decrease in basicity, and second effect is chemical twins are prepared. So remember these two effects of lanthanoid contraction. It is not expected to write in detail how these chemical twins are prepared, then what is why these atomic sizes and ionic sizes of the post lanthanoids are decreasing. You know, due to the lanthanoid contraction, this is happening. Atomic sizes become similar. So remember this word, chemical twins. This is asked for the examination, for the competitive examinations it is asked, and these are the pairs. Zirconium, hafnium, NbTA, molybdenum, tungsten, and this is a TCRe. For 1 mark, they can also ask the question, what is mean by chemical twins? Write 2 examples of chemical twins. So any 2 examples we can remember this. Then I'm coming to the last part of this lanthanides. Applications are given. Applications of lanthanides. So this lanthanides which are used in the inert surface of the television tube or computer monitor, it is coated with tiny patches of 3 different lanthanoids. So there is a combination of lanthanoids which is used inside surface of the television tube or computer monitor, which is a composition of to give 3 colors that make the color image. So for the preparing of color image, these lanthanides are used in television tubes and color monitor. But nowadays the displays are changed. LCD displays, LED displays are there. I don't think this is used nowadays, but in case of old days, the CRT monitors are there, the cathode ray tubes are there. So collect the information of this nowadays, which elements are used for preparing this color image, 3 color image. So these lanthanides are the mixture of mixed oxide of europium, then yttrium, and which is a yes, these only 2 lanthanoids are used. One is europium and one is yttrium. They combine together. And they releases the 3 colors. Remember, they releases the 3 colors. These combination of europium and ytterbium. This combination is given here. If you remember the combination, it is well and good. If you forgot this combination, don't worry. remember these names only, europium and yttrium. They combine together and they releases an intense red color. So this is one use of these lanthanides. Then also in case of optoelectronic, these are related to eyes. So optoelectronic applications uses lanthanide ions are active ions in case of luminescent material. For example, this is given Nd. Nd, this is a neodymium. Yag. Y is for yttrium, A for this aluminium, and this G for garnet. So this Nd Yag laser, once again I am repeating this Nd, it is a neodymium. This Y for yttrium, this A for aluminium, and this G for garnet. So NdYag, this is used for optoelectronic applications, remember. Then this RBM doped fiber amplifiers are significant devices in the optical fiber. For the communication system, these lanthanides are also used in hybrid cars, superconductors and permanent magnets. Then one important use is given mesh metal. Mesh metal, it is a mixture of lanthanum, iron, then some small quantities of sulfur, carbon, calcium, aluminium. This is alloy. Alloy means there is a, we already discussed about this alloy in case of transition elements. Alloy means it is a mixture of the metals having the similar atomic radii. It is randomly distributed. So this alloy, mesh metal, it is alloy, it is used to manufacturing of bullets, means bullets and shells. Means outer surface of the bullets, it is prepared with this mesh metal. Remember? So this combination, remember this combination, it is asked for the competitive exams like CET, like JE, like NEET exam, mesh metal. So remember this lanthanum is there, then iron, then traces of sulfur, then carbon, calcium, aluminium. These are used for the preparation of bullets and shells. So remember this mesh metal for the competitive exams it is asked. It is not given in your textbook, but I have given this for the extra knowledge. Then I am coming to the actinides. So the lanthanides and actinides, these two series are the A block elements. Lanthanides part is completed. Now I am coming to the actinides. In case of actinides, it starts from 89 and ends with 103, that is thorium. Sorry. Again, I am coming to the periodic table. See. This is the periodic table 89 to 103. One printing mistake is there. So actually it is a 90 to 103, 89. This is a thorium having the atomic number, you can see 90. See, 90 to 103. So this part is completed. Yes, this actinides begins with actinium actually, but these are the 14 elements from thorium to lawrencium. That is atomic number 90 to atomic number 103. Again, there are 14 elements. These 14 elements collectively called as actinides. Most of these elements are not found in nature. They are man-made compounds. They are all radioactive and man-made. Those elements having the high densities, high melting points, also having the high boiling points. more than 3000 degrees. This is the boiling point, and melting point is also high. Actinides are less reactive than the lanthanides. These are the some general properties are given. This is not asked for the board examination, remember. For example, they react with hot but not cold water to give the hydroxide and hydrogen gas. So the reactivity is very, very less. Actinides are less reactive than the lanthanides, so they react with hot but not react with cold water to give hydroxide and hydrogen gas. Then, unlike lanthanides, they exhibit oxidation numbers in their compounds, which varies from +2 to +8. So the definition of actinides is given here. The series of the elements from this thorium 90 to lawrencium 103, in which the 5f orbital is progressively filled. And in case of lanthanides, 4f orbital is progressively filled. But in case of this actinides, 5f orbital is progressively filled. This is called as lanthanides. For the definition, it is important. Then this is the electronic configuration. It is shown. Atomic number is 89. Atomic number is 103. This is the electronic configuration with respect to inert gas. It is shown radon. And then this is a 5f0. This is a ground state electronic configuration. This is in +3 oxidation state. We can see this ionic radii is also decreases. This is called as actinide contraction. And this is a general electronic configuration is shown. It is similar to the lanthanides also. In case of lanthanides, it is the xenon 4f0 to 14. So in case of actinides, it is radon. 5f is given here. Remember, in case of actinides, electron enters in 5f 0 to 14, 6d 0 to 2, and 7s2. So in lanthanides, it is 6s2 and it is 5d and it is 4f. So in case of actinides, one shell is increased, it is 5f, it is 6d, and it is 7s. So electron enters in n minus 2. So n is here 7, n minus 2 becomes 5. So the electrons enters in pre-penultimate shell. This is a pre-penultimate shell. This is a, we can see last shell. And this is a penultimate, 6d is penultimate, and 5f, it is a pre-penultimate. So as it is inside the d orbital, these are also called as inner transition elements. Transition elements के जो पहले inside है, अंदर है, it is called as inner transition elements. So with this general electronic configuration, it will be clear. So 7 is the last shell, 6d is the penultimate shell, and 5f is the pre-penultimate shell. Remember. So electrons enters in pre-penultimate shell. So don't worry about the atomic numbers. Electronic configuration, it will be not asked on this lanthanides and actinides. Contraction, it is many times asked for the board examination. These properties are also not asked, but I will explain these properties. They appear in silver white in color. They are highly reactive radioactive elements. Remember, all these elements are radioactive elements except promethium. All are non-radioactive in nature. Then they experience the decrease in atomic radii. This is called as actinide contraction. Remember, they usually exhibit, they also exhibit +3 oxidation state. Lanthanides also exhibit +3 oxidation state. Oxidation state detailed I have explained. So this lanthanide contraction is the given. It is having the same definition. The atomic and ionic radii of actinide shows a decrease in atomic radii with increase in atomic number. It is called as actinide contraction. So these applications are given. It is not asked for the examination. And